Yeah, thank you for the introduction. I'm going to talk about some of the work and some of our experiences here in Minnesota developing biological criteria for protecting aquatic life. I'm going to basically talk about our journey in developing the biological condition gradient of BCG, using that to develop biological criteria, and I'll also get into the adoption and implementation of tiered aquatic life uses and how the BCG fits into that. So just to start off, wow, that's interesting. Oh, that's quite. Let's try that again. All right, let's try again. All right, so basically the foundation of the work that we're doing here stems from the narrative language that we find in the Clean Water Act, as well as in our state rules, which basically lay out the narratively what we're supposed to be protective of in terms of aquatic life. And of course, there isn't a lot of specificity in this language, and so that's really what I'm going to talk about is how we went about looking at this, taking this language and developing numeric biological criteria that would be protective and consistent for aquatic life. So, for those of you not familiar with Minnesota, it is naturally a fairly diverse state. Looking at the vegetation, we have in the west and the south prairie regions. In the north, it's more forested. In the middle, you have mixed forests. So you have some fairly strong natural gradients within the state that we needed to address. But there's also anthropogenic gradients across the state. And just to confuse things, those natural and anthropogenic gradients are often confounded. So the prairie region is now mostly row crop. Forested region is still mostly forest, and that's where we find the less disturbed watersheds in our state, and we have everything in between. So one of the first things we did was develop indices and biological integrity, and those are the tools that we use for measuring fish and macroinvertebrates in the state. And across the state, we have 9 classes that break out by river size, gradient, region, thermal regime. And these are really to address those natural gradients. We want to compare a northern cold water stream community to a southern river. They have naturally different communities. So these IBIs address those natural differences, those natural gradients we see across the state. And we have similar framework, although not fully aligned, also for the macroinvertebrates, but also 9 classes, or 9 types of stream. So with these IBIs, we go out, we collect the fish or the bug data, we sort and identify what's there, it produces a taxa list. Those metrics are calculated. There's each of those 9 IBIs for both assemblages. There's a different suite of metrics. So there's 18 different models for stream biological communities. And so we calculate these metrics that measure different aspects of the community, feeding, sensitivity, life history traits, and so forth. And that information is distilled down to an IBI score, which is a scale of 0 to 100. And so we get a score, and then the question is, what score is in attainment of the Clean Water Act minimum goal, in attainment of Minnesota's goals in terms of aquatic life. So we get a community that meets a 16. Is that meet goals? 55, 87. What is the IBI score that's consistent with attainment of our aquatic life beneficial uses? So the first step that we used, or the first way to get at this, was to use a reference condition, and this is commonly used in the U.S. anyway. We developed a human disturbance score, which measures essentially the amount of human activity there is within the watershed. So, how many point sources are in the watershed, what percent of the land use is agricultural, how much of it is developed or impervious. And you get a score of 0 to 80. 80 is basically undisturbed watershed, with 0 being obviously heavily disturbed. And we basically just, chopped this HDS range into 4 parts and said, well, if it's in that upper quarter of the scale, it's going to, probably have minimal disturbance within the watershed, and that's usually what bears out when you look at these watersheds. So we had a way to identify reference sites. So we then looked at our data set, and as you can see, once you look at just your reference sites, we don't have a whole lot of reference sites in the south region. And even when you do have maybe enough reference sites, you have a lot of pseudoreplication. We have a lot of basically sites on the same river representing your reference condition. So there's questions as to how well does 10, 15, 20 samples, how well does that represent the reference condition within that stream type? I don't know why I did that again, but give you a little preview. Another issue with that is with small sample size is estimating something like 25th percentile with your reference condition for your IBI scores. When you're below 30 or so samples, there's a pretty wide range, or you have a pretty low amount of confidence in that value representing that true population site. So there's a number of reasons why we want to make sure that those reference sites are representative of that attainment of that beneficial use. Another issue is when you look across the state, do those different reference populations, do they mean something different? So in the north, we're pretty confident that those are minimally disturbed reference sites. When you look at those sites, they are pretty high quality. There's not a lot of human activity, but as you move into the more heavily disturbed watersheds, your biological condition is probably more in the least disturbed range, which means if you're using those populations of sites to set your thresholds, they're going to mean something different depending on where you are in the state. And so we wanted to avoid having these different protection levels when we set these aquatic life use goals. There's a number of ways you can get around them, and other states have done this. You can look at using different criteria for your reference sites, or you can use different statistics. So rather than using the 25th percentile of your reference sites, you could use 50th, something like that. But we looked into using the biological condition gradient to maybe solve some of these issues. So if you're not familiar with the BCG, it's a framework for interpreting how biological communities change as the amount of stress increases. So on the x-axis here is the amount of stress. On the y-axis is biological condition. High biological condition, these are basically natural, undisturbed communities. As that stress increases, it slides down from BCG level 1 down to 6, where you see major changes in the biological community. So the development of it I'll talk about, but it's based on a combination of ecological theory and empirical data. We felt that it would be supportive of our biological goal development. And another nice thing about it is that it provides a framework for communicating what your biological goals actually mean when you're talking to the public or policymakers. So we embarked on this. I do not know why it's so we embarked on this process. I've already talked about the first 2 bullets there, the classification, and that's our IBI framework. There's 9 different classes. The stressor gradient, that's our human disturbance score. So we've taken care of that up to this point. And so then we held workshops. And in these workshops, you have a panel of experts. In our case, a panel of fish experts or a panel of macrovertebrate experts. And Ideally, you're going to have experts from different agencies, different states, different tribes, so that you're getting a diversity of expertise coming to these workshops. And so you go through these workshops, and I'll step through the actual steps of you go through the workshop, and then following the workshop for developing the models and developing a model that actually replicates the decisions that a panel can make. So the first step is to assign attributes to your taxa. So once you've convened your panel and you start looking at individual taxa, and based on their expertise and based on data like what you're seeing here on these graphs, you're assigning taxa to one of these 6 attributes. And there's 4 other attributes in the BCG, but most BCGs really only focus on these 6, and that's what we did. So you have these attribute 1 taxa. These are kind of these really special sensitive taxa. The example here is caddisfly Dolophyloides, where the x-axis on these plots is disturbance, to the left-hand side, lower watershed disturbance. So this species is really only found in watersheds that have the lowest disturbance in our state. But they could be other things. They might be endangered species. It might be long-lived species like sturgeon, for example. So there's sort of these special taxa that are usually indicative of high-quality systems. Then you have highly sensitive taxa, specialist taxa, taxa that drop out as disturbance increases. So they persist perhaps a little bit longer than those historically documented sensitive taxa do, but they're still fairly sensitive. Then you have attribute 3. These are sensitive but more common. They'll persist even further down that gradient, but they still show a response to disturbance. Attribute 4, these are taxa of intermediate tolerance. So these taxa, either they seem to be most common in the mid-range of disturbance, or they don't really show any response at all. And then attribute 5, tolerant taxa, taxa that actually decline as disturbance decreases. And when we did this for fish, we actually divided the tolerant taxa into 2 sub-attributes. There was tolerant taxa and then very tolerant taxa. So we felt that we could get a little more information out of these taxa when we developed the models. And then you have non-native taxa, which is pretty straightforward. They tend to be tolerant taxa as well, but not always. So again, with the fish models that we developed, the non-native taxa were actually broken up into 2 groups. There's sensitive non-native taxa. In particular, we have stream trout, rainbow trout, and brown trout, which are actually fairly sensitive, although they're not native. So, as opposed to something like carp, we wanted to make a distinction between the facts that some were sensitive and others weren't. So once you have these attributes assigned, then we start assigning BCG levels to individual samples. So here's an example of a sample. You've got a list of taxa, how many individuals were present in that sample of each of those taxa. And then there are those attributes I just went over on the left-hand side, as well as some summary information regarding the number of taxa for each of those attributes, or percent of taxa, the percent of individuals. And basically, the panel's looking at this information. We're working to build a consensus as to where this community falls on this biological condition gradient. And basically, for each of those stream types, we're shooting for 30 or more samples across a range of stress, so that we can, as much as we can for that stream type, fill out that biological condition gradient. In the process of going through that exercise, we're trying to elicit information from the panelists as to why they're making decisions for why a sample is say a BCG2 versus a BCG3. Are there not enough taxa present, or would you expect to see more brook trout or more stoneflies present? Are there too many tolerant taxons? So we're looking at what kind of attributes or what kind of features within that sample the panelists are responding to, and so then after those metrics, we can actually look at how these metrics array along a gradient along that BCG gradient. So the x-axis here shows BCG 2 through 5. This class, there was no 1s or 6s. But you can see for this attribute 5% taxa, so those are the tolerant taxa, as as you go down that gradient, those tolerant taxa become more common, or there's more, at least there's more taxa, or at least there are a larger percentage of those taxa. And you can see BCG2, that stands out, that looks different from 3, looks different than 4. Maybe it doesn't do a great job of distinguishing between 4 and 5. Something like this ephemeroptera percent taxa doesn't really seem to show much of anything. So you're going through and analyzing the data to try to identify metrics that do a reasonable job of distinguishing between these BCG levels, because I'm going to talk to someone about this keyboard. Because you want to develop a list of decision rules for these different BCG levels. So in this case, this is a rules for our cold water fish BCG model. And so there's a series of rules that are needed in order to for a site to be considered a level 1 or a level 2 and so forth. And basically it works like a cascade. So you take your sample, you calculate the metrics for that sample. It needs to meet all of those metrics. If it does, then it would be assigned to BCG level 1. If not, it would drop back down. It would drop down to 2. You check those metrics. If it meets, then it'd be 2. If not, it would drop down into continue until you find the level where it meets all of those rules. You'll notice that the rule criteria, they're actually a range. This is because it's based on fuzzy set theory. So there's basically what this means is once you assign a BCG level, it usually doesn't assign 100% probability of belonging to that level. It'll say, well, the sample is 60% BCG level 2, 40% BCG level 3. And this matches what we see when we go through these exercises, in that basically panelists will say, well, that BCG level, that's a level 3, but it's not a grade 3. It's moving toward a 4. So even though we're bidding these things, there's a gradient within these levels, and the fuzzy set model will actually pick some of that out, recognize that there is a little bit of fuzziness around some of these decisions. So this just shows you the BCG scores for our fish samples across the state. As you'd expect in the north, it's 1s, 2s, and 3s for the most part. You get into the prairie region, see more 4s, 5s, and 6s. So with these fuzzy set models, we can collect data and run them through the model, and basically have a pretty good confidence that it replicates the decision that a panel would make. And the reason why that's advantageous is because it's often difficult to get 6, 10 experts together in a room to spend many, many hours rating these sites. And Minnesota, we collect between the fish and the macroinvertebrates on order of 500, 600 samples a year, and so it's not feasible to get a BCG score from all these from the panel. But the other advantage of actually having these rules is makes the decision-making process for assigning BCG levels transparent. So, going back to the development of the biological criteria, basically, once we develop these BCG models, so there's 18 total BCG models for streams, we can look at again, those reference sites, and basically it confirms what we thought, and that's, again, there's very few sites that are reference sites in the southern stream types, and they tend to be more in that BCG 4 or 5 range. So this was something that we discussed when we were developing the models. You know, where is that aquatic life goal? Some said, well, maybe it's in 3, others it's in 4, but certainly by the time you get to 5, that's probably not attainment of the Clean Water Act minimum goal. So what this basically confirms, what we suspected is that we have lower biological quality or biological condition within these southern stream classes compared to the north. And even in some of these other classes where we do have more or better biological condition, these low gradient streams are actually a statewide class. The southern cold water streams, a little higher quality. It's in a forested area in the south. They still tend to be a little lower in terms of biological condition than those northern stream classes. Same is basically true of the invertebrates. There's just, in general, there's a small number of these sites, and they tend to be shifted down that BCG level. So we have this concern that if we take these IBI distributions for the reference sites and calculate 25th percentile or some other statistic, that we'd be setting the bar differently. And that's basically what the BCG is telling us. And so if we say we're going to use the 25th percentile, the northern rivers are going to be much more protective than the low gradient streams, and even more protective than the southern headwaters. And particular concern is the fact that something like the southern headwaters, they're down in this BCG level 5, where we're not comfortable in saying that BCG level 5 is attaining aquatic life use goals. So what we did was pretty straightforward. We just looked to those reference sites where we were fairly confident that they represented the minimally disturbed conditions of northern stream types, and looked at how they related to different statistics on that BCG. And long story short, basically the meeting the BCG 4 fell out as being closest to that 25th percentile, or at least falling in between the 5th and 25th percentile, that reference distribution. And based on discussions that, the BCG level 4 is probably consistent with attainment of those goals. We have narrative language that indicates that the ecosystem functions are largely maintained. You've basically just lost some of your sensitive taxa and have been replaced by more tolerant taxa that fill similar ecological roles. So we felt that that was defensible in terms of a goal that supports aquatic life uses in the state. So basically, the way this general goal arrays on this gradient is in the middle of that BCG 4 level, so BCG level 4. So the other nice thing about the BCG, other than we now have a tool that we can go out and assess attainment or non-attainment of our goals, is that there's additional information that's bound up within that BCG level. So, and you can look at it at different scales. So BCG level 2 has narratives associated with it. Ecosystem level functions fully maintained, but some changes in taxa, biomass. There's further details, regarding executive taxes that are present. So we've used the BCG information internally and externally to explain, how these biological communities are performing on this natural gradient, not just the gradients of what is left within that stream type. So that's how we arrived at our basic Clean Water Act interim goal or Clean Water Act minimum goals for aquatic life efficient macroinvertebrates and streams. One thing, though, that we were concerned about, because there is a pretty strong anthropogenic gradient or biological condition gradient across the state, where we have streams like the West Branch River up on the northeast part of the state that are that BCG level 1, BCG level 2. They're pretty close to being natural conditions. So they're doing much better than that general use goal. They're well above that BCG level 4. So they're well exceeding our general use goals. Other streams like the Little Cedar River, which it's in an agricultural watershed, but it's doing pretty well. It's just above that threshold. So maybe that general use goal works okay for this type of system. But then we have other waters like Judicial Ditch number 7, which is a ditch. It has poor habitat. It doesn't meet that general use. And basically the reason why it's not meeting that general use is because it's maintained for drainage. And the removal of that habitat diversity within the system more or less precludes the ability of that stream or ditch to meet a goal that a natural river goal, more or less. So in October 2017, we adopted tiered aquatic life uses, which actually divides our biological criteria up into 3 tiers. So we have an exceptional use tier for those really high quality waters that are doing much better. The general use, which is that the Clean Water Act interim goal, and then a modified use, which is below that minimum goal, which means it has to go through a use attainability analysis. But given its maintenance for drainage, it's not reasonable to expect it to perform as a natural stream does. And the BCG played a role in developing the biological criteria for each of these tiers. I already talked about the 25th percentile, the reference sites, the median BCG4 being used for the general use. We used a similar approach with the exceptional use. It's basically the 75th percentile of those BCG3 sites, and then the modified use falls at the median of BCG5. So this is where those thresholds array along that biological condition gradient. We have a matrix of biological criteria for those 3 tiers for the 18 different stream types in the state, which we can now apply to these streams and basically apply goals that are achievable or attainable. One thing to note is that the modified use, we don't have biocriteria for all of those streams. Basically, the rivers, the large rivers, and the cold water streams don't have a modified use. And this is because there aren't many ditches in these stream types, and even when they are channelized, they often demonstrate an ability to meet that general use. So the other elements of the BCG that was useful is that, again, we can use the language that comes with that model to communicate what we mean when we talk about exceptional, general, or modified use. This language is actually codified in Minnesota rule, as well as the supporting biological, the BCG model reports. Those are also incorporated by reference into our rules. So you can step through that information and use that to describe exactly what we mean by attainment of each of these 3 beneficial uses. So the way these the tiered uses work, it's similar to how the uses worked when you just had one size fits all, the general use. Now we've got different options. So if you have a stream that's designated as an exceptional use and it's degraded for some reason, now it goes below that general use threshold, although it's still above that general use goal. So under our old framework, if you had this happen, it would still be an attainment of our aquatic life use goals, but because it's been designated as an exceptional use, that's been established as an existing use. So that fish community would need to be restored back to that exceptional use goal. So it becomes impaired and would go on the 303D list. Same would be true of general use or modified use goal streams. If they decline below those thresholds, then they would be impaired and would need to be restored back above those lines. So basically, it gives you more options in terms of the management of these systems, and it's tied to what's achievable or attainable. They can't go down below a line, below these thresholds once it's been established that that's an attainable goal, but they can go up. So that's the hope, or the objective is over time, modified uses will become general uses and general uses will become exceptional uses. How do we go about actually determining these tiered uses? It's largely, or at least primarily, driven by the biology. So the first thing we're going to ask is whether or not those general or exceptional use biological criteria are met. So if a stream meets the general use biological criteria for the general use, then it's going to be a general use stream. If it's doing better than that, if it meets the criteria for exceptional use, then we get designated as exceptional use. Because meeting those uses, so those uses are demonstrated to be attainable. However, if we determine that the general use is not met for one of those assemblages, and that triggers a use attainability analysis. And the first thing we're going to ask as part of that UAA is whether or not the habitat is limiting those biological communities, and that determination is based on habitat data that we collect at the time of fish and macroinvertebrate sampling. We have a series of models. These are logistic regression models that look at the probability of meeting that general use biocriterion based on habitat conditions. And we usually use a threshold of about 25% being, if it has less than a 25% probability of attaining that biocriterion, the habitat is likely to be. And so, but if it's not, if the habitat looks pretty good, models indicate the habitat's not limiting, then it would get designated as a general use. And this would go for ditches. So we have plenty of ditches that have good habitat that would be designated as general use. The next question is whether or not the habitat is a result of legal human activities. And there's a lot of questions rolled into this, and I'll cover a couple of those. But I mean, one obvious one is that it isn't a ditch. It's not. We have natural channel streams that have poor habitat, and that may be part of what's driving the non-attainment of that general use. But if this or another reason, basically if it's not those legal human activities, then we would designate it as general use. But if the answer is yes, then it could be eligible for a modified use. So just to go through a few examples here, these are all channelized systems in Minnesota. This top three, these are ditches, but they've got good biology. The biology meets the general use, so that's a ditch that's going to be designated as general use. These, the ditches on the bottom, those are, they have poor biology, but the habitat isn't limited. So there's something else that's limiting the biology based on our models besides the habitat, whether it's a chemical issue or a hydrology issue. There's something else that's driving the non-attainment of those communities, and so they would be designated as general use. Here's a couple of ditches. They're straight as arrows, but they've got some really nice habitat in them. Good substrates, macrophytes. So these are basically our general use ditches. One of the other things we consider is restorability. So if we look at this stream, it's the green segments are natural portions, so natural channels. The red segments are channelized sections. So we've got a biostation that's on one of these channelized sections. And because it's relatively short, we don't want to chop this, a tenth of a mile, 2/10 of a mile section out of this stream and call it a modified use. We recognize this as being something that's potentially restorable, given the fact that it's short and that it's in an otherwise natural channel system. Another consideration that we make, so we do a lot of remote sensing, a lot of reviewing aerophotography to make sure that we're being consistent with existing use. So we want to make sure something was ditched on or after November 28, 1975, the existing use date. So here's an example of a stream that in 1976 was natural. By the time we got to it to sample it for biology, it had been channelized, but we because it was natural after that 75 date, wouldn't be eligible for a modified use. This is the more typical scenario for a modified use, a watershed system where all of the streams have been straightened, or these are constructed ditches where they drained wetlands or upland areas, and they have very poor habitats for biological communities, and they're essentially continuing to be, in many cases the ditching goes well before 1975, and they are continuing to be maintained for drainage. So we have this tiered framework. It's based on these biological criteria derived from the BCG. Some of the implications that we have are considerable. So with a modified use, this is a map showing the stream miles that are altered, for the most part ditched, natural or impounded. And as you can see, there's a lot of red in Minnesota. So we have actually more miles of ditch in the state than there are natural channel streams. So we've got a lot of ditches. So it poses challenges for managing these systems in terms of the biological communities that they can support. So, the adoption of the modified use means, yes, in fact, we will have fewer impaired waters because we'll have some of these ditches that are modified uses that meet that modified use goal, but not the general use goal they would have had to meet before we adopted TALU. And there are still quite a few that are impaired, but when they are impaired, we can set attainable goals that are in line with what can be achieved within a system that's being maintained for drainage. It doesn't have the habitat for biological community. So here's an example of a heavily ditched watershed, the South Fork of the Crow watershed. Basically, there's one stream in this watershed that meets the general use. Everything else is below that. So under our old framework, everything else is impaired. Under TALU, we do have a relatively small portion of the watershed that would be full support based on those modified use goals, but still more than 50% of those streams are going to be impaired modified uses, along with quite a few impaired general use streams. The exceptional use waters, those are just the opposite. So in the far north, we have the Lake Superior watershed here. More than a third of the streams that we've monitored within that watershed fall into that exceptional use category. And so the strategy there is a little bit different. Basically, you have systems that are meeting your goals, so you're shifting toward protection strategies. So we're trying to do more besides just restoration. We're trying to bring in protection strategies, and that's part of the reports, which are called RAPs, or Watershed Restoration and Protection Strategies, to try to protect these, but they may also be protected through anti-degradation or site-specific standards when necessary. So these are some preliminary designations. We have to go through a rulemaking to designate anything as a modified or an exceptional use. So these are just based on our, back of the envelope reviews, looking at the data that we have. And as expected, most of those exceptional uses are in the Northeast. There's some down in the Southeast. There is a fair bit of forest and a lot of groundwater, cold water systems. Most of the modified uses are, as expected, out in prairie regions where we have quite a lot of ditching. So the way that we implement the biological criteria and the tiered aquatic life uses is through what we call intensive watershed management strategy. We have 80 huts in the state, and we monitor roughly 8 of those every year. So the intent is to go through the entire state on a 10-year cycle. The monitoring data that we collect is collected to support the assessment of the biological communities as well as those use designations, those UAAs. So that's the first step after we collect our biological, chemical, habitat data, is to determine which of those 3 tiers the stream falls into. And we also review classification. Is it a cold water or warm water stream? Because getting the designation right determines the outcomes of the assessment. And that then impacts all the steps that follow afterwards, including the stressor identification, the TMDL, and those watershed restoration and protection strategy studies. And then, of course, all of the activities that we do in the watersheds to protect and restore these systems. And after a 10-year cycle, we're back to monitoring to see if all of the activities that have taken place are, doing what they should be doing, and we're moving in the right direction. If not, then we can use the information collected in the next cycle to try to make corrections. So I can't tell you that TALU or the BCG biological criteria that we've developed work perfectly. That's something that maybe after we've gone through 2 cycles of our watershed monitoring, we can start to answer some of those questions. So you can get back to me in about 16 years, but there are other states who have been using tiered aquatic life uses and also criteria that are more or less derived from the biological condition gradient. Ohio, as an example, has had TALU for many decades, or several decades anyway now. And they've seen their full attainment for their aquatic life uses go from about 46% to 59% from 2002 to 2014. Maine is another state that has TALU. They've seen an increase in those streams that are assigned their highest use class, more or less equivalent to Minnesota's exceptional use. So you see a lot of the green turning to blue as they move more of these streams into that higher class. So at least for these 2 states, this type of framework has been effective for them, and so those are the sort of results that we're hoping to see in Minnesota over the next couple of decades. So just to summarize, the use of the BCG and how Minnesota has used it, it can be a helpful yardstick so that you can compare sites or stream classes, either across regions, states, because different programs are going to collect different data. You're going to have different ecoregions and so forth, and so everyone's got their own model. They all sort of tell you something different, and it makes it difficult for comparisons. So, it'd be helpful to be able to make comparisons across programs. But just for Minnesota, we found it useful internally to deal with those differences, where we had these strong anthropogenic gradients across the state. It allowed us to set those criteria that we felt were protective. We're going to be in line with the Clean Water Act's minimum goal, and to develop tiered aquatic life uses. And this was particularly important for those regions, the prairie regions, where there was a high level of disturbance, and that reference condition really isn't extant. So the BCG gave us a way to see where those streams stood and to develop biological criteria for those regions. And it's also helpful with communicating these goals. So like I said, the BCG factors fairly heavily within our rules. The BCG language is directly written into our rules. So you have that, you have the supporting documentation so that we can go back to that when we're talking about what these goals actually mean in terms of aquatic life conditions. So that's all that I have. A little bit of contact information. Imagine I've got plenty of time. So, and if anyone wants to contact me offline, I'm happy to talk about this further.